So in the previous video we talk about the basics of the buck converter, and in that analysis, if you recall, what we assumed is, if this is inductor current, we assumed it starts with a non-zero value. Let's call this I0. Then it goes to some maximum voltage. Let me draw the circuit here as well. So when you close the switch, that inductor is charging, and here we have the inductor current. And at the steady state, if this is some non-zero current, then it charges up to some value. Then during discharging, you have the same value because it is operating under steady state condition. So here, whenever it is on, whenever that switch is on, you are charging the inductor. So basically you are transferring some energy from source side to the inductor, and in the second half your inductor, while it is discharging, yes, the inductor is discharging, but it is still charging your capacitor. So the power flow in the second cycle is from your inductor to your capacitor, and from your capacitor to your load. Anyway, so what would happen? What will happen if we reduce our load? Okay, if we reduce our, now let me say not I out, this is I0. Let me make difference. So anyway, if you reduce your output current, so let's say you have a resistive load, maybe that resistance is going up. So obviously the average current is going to come down. So instead of having that kind of waveform, so you will have maybe that kind of waveform. Then after that you will have that kind of waveform, and you expect, if we reduce it down and down, you may assume maybe you end up with a waveform like that, right? But again, this is not possible if this is IL. It is not possible because the inductor current here, it cannot flow in that direction. Okay, whenever that is off, and that diode cannot carry current in the reverse direction. So it is not possible to have that kind of negative current. So what would happen? What would happen when we reach to some zero voltage? It will not go down, but it will stay at that. Let me use my red. So it will stay at that zero current. So this is called, maybe you can remember it from the previous week. So the first one is called continuous conduction mode. Okay, let me write it here. Mode, or CCM in short, CCM, where the current, for this topology, the current in the inductor is always positive, so it doesn't stops conducting, so it is continuous conduction mode. However, if you have that kind of waveform, if you let me draw it here, if you have, I don't know, that kind of waveform where it touches here and you have IL is equal to 0 for some time, this is called discontinuous. Okay, let me write discontinuous conduction mode, or DCM in short. Okay, so DCM is not a bad thing, but the characteristics of our converter changes, so we need to be careful about our calculations. And the previous derivation that we say V out is equal D times V in is only valid for continuous conduction mode of operation. So again, there are some controllers or converters which can operate DCM mode, or even they can prefer to operate in discontinuous conduction mode, because if it is designed properly, DCM can result in higher efficiencies. So let's find Okay, again, it's not a bad thing, but we need to change we need to at least understand that transition because our output voltage equation changes. So let's try to find the instant where we moved from CCM to DCM. Okay, so that instant is, yes, you can start with that kind of current, and that current gets smaller and smaller, either with changing your resistance or maybe your input voltage is changing. So anyway, so we would like to find the instant where we moved from continuous conduction mode to discontinuous conduction mode, and that mode is where when the inductor is discharging, it just touches the zero. So I initial or I at TS will be equal to 0 amps, and at that instant then you are charging it again. So the point that it touches at that point will be the transition to DCM. So how we can find that transition? So let's make some definitions, and the peak of our current is IL peak, and then we have the average voltage, and let's call it IL bond B or IL boundary. Okay, boundary, and it can be shown as like IOB. Anyway, so then the final current is going to touch to 0. So we have more space. Let me write that ILB, okay, the boundary current. Again, it can, here you can see the triangular shape, and you can say the average, the average current for that one will be half of that peak current. IL peak divided by 2 is my boundary current, and I want to find the value of that current. Okay, and what is that maximum current? So I can find it because it just starts from here, and I can, by the way, that square waveform is the inductor voltage. So I know the inductor voltage, which is equal to VD minus VO from the previous slides, and I can calculate how much the current increase, and it starts from 0 at steady state. So let's write that one. So ILB, okay, ILB is equal to IL peak divided by 2, and IL peak is equal to T on, okay, T on times VD minus VO divided by L. Why? And let me write it in the long form. You can write, IL is equal to integral VL dt plus I0, and here, the integral, it is a constant waveform. It is VD. I forgot to write 1 over L here, I0, and it is 1 over L times the integral here is VD minus VO, and during how much it is T on, so this is equal to IL peak. So I can write that term directly here, and the average will be the half of that thing. So that is my boundary current. And of course I can write in terms of instead of T on, I can write this one is DTS. So IL boundary is equal to D time TS VD minus VO divided by 2L. Okay, and basically let's write that equation in terms of, let me clear that part a little bit. So it is still in the continuous conduction mode, so I can write the V output in terms of write it here, V output is equal to D times VD. So this time equals to ILB is equal D time TS times 1 minus D times VD divided by 2L. Okay. So that defines the boundary calculation. So let me write it here, and let's have a look at that equation. So if D is 0, our boundary current will be equal to 0. If D is 1, again our boundary current will be 0. And where does it have the maximum boundary current? When that that all boundary current is maximum when D is equal to 0.5. So let me show you the equation. And actually, if you put let me write the previous equation, and if you write 0.5 here, you have 0.5, you have another 0.5, and it is divided by 2L already. So the maximum boundary current that you can have is TS times VD divided by 8L, and when duty cycle is equal to 0.5. So what does it mean? So let's have a look at the graph. Okay, have a look at the graph. So this is the boundary current. Okay, so whenever your current is less than that value, okay, so that side is discontinuous conduction mode, this area under that one, and here it is continuous conduction mode, and this just shows you the boundary between your continuous conduction mode and discontinuous conduction mode. So again, it's not a bad thing to operate in the DCM mode, but if you want to, let me rewrite that one, TS is equal to 1 over S, so VD divided by 8L Fs. Okay, so if you want to operate at a higher boundary current, either you can, or let me show the other way, if you want to stay in the continuous conduction mode longer, okay, if you want to operate in the continuous conduction mode for even small currents, what you need to do is either you can increase the L, which you can use a larger inductor, or you can use a higher switching frequency, or you can reduce VD. Okay. There's also another relation between the minimum inductance that you should have for continuous current. So from the previous slide, we know the boundary current is equal to D times TS times VD 1 minus D divided by 2L, right? So let's derive that equation. So here I would like to get a relation for the L. So let's move L here, and I have D TS VD 1 minus D divided 2 IL boundary. And remember, this was the average current. So here, D and VD, they are equal to VO. Okay, and if you divide VO by ILB, okay, ILB was the average, remember, inductor current, and which is equal to load current, because they're in the steady state, so there is no net energy storage in one cycle. So I can write that one as V divided by R is equal to R load. So it is TS times 1 minus D divided by 2 times RL, the output load, or instead of Fs, instead of TS, I can write 1 minus 1 divided by Fs. So it is 1 minus D divided by 2 Fs RL. So this is, the minimum inductance that you need to have for continuous current. So let's have a look at that one. So again, if you somehow increase, that is important, if you increase Fs, then it is possible to have a smaller inductance. Okay, so that is, one of the common relations. By increasing the switching frequency, you can make the inductor, or as well we will show the capacitor, smaller. But again, increasing Fs is creating more losses on your semiconductor, so you need to be careful about the efficiency and the thermal management. But that is, here, that is the way to reduce the size of the converter. So you can reduce the size of the converter by increasing switching frequency. Again, if if resistance is increasing, and again you can say if R is increasing, that means load is reducing or current is reducing. So if you want to operate at lower currents in the continuous conduction mode, then you need to use a larger L. And in some applications, the ripple in the inductor, remember the waveform, the ripple, if this is IL, again, this is not only for boundary range, but this is for operation. So you can have that inductor ripple. So how can you calculate that? So you can either use the charging or discharging. So let's use the charging one. So I would like to see what is the ripple at IL. So what is that period is the TS, and I will use the same equation. So IL is equal to again I forgot the inductor, 1 over L integral VL dt plus I0, or if this is, let's say, I final, if this is I0, let's call IF. So IF minus IO, which is equal to delta IL, is equal to 1 over L VL dt. And during that on transition, remember it was Vs or Vd, Vs minus Vo, it is the inductor voltage, or Vd, divided by L, and it is constant, and it is dTs. Again, I can rewrite that equation like here, and you can write, instead of Ts, you can write 1 over Fs. So it is that equation. So again, if you want to have a small ripple in your inductor, either you can use a higher inductance size. I mean, that makes sense. If you use a larger inductance, the current ripple will be less. Again, similar to the previous case, or you can increase your switching frequency, which has other disadvantages, but again, we can reduce the ripple by increasing the switching frequency. Or, again, the output voltage has a relation with the ripple. So again, that ripple is not constant, and it is changing depending your duty cycle and operating condition. So let's have a look at what will happen if we move to the DCM mode. So now we are not in the boundary condition, but we moved further into discontinuous conduction mode. Again, there are some details and derivations in the textbook, so you can have a look at for the equations in the textbook. But let's discuss the basic relations. Okay, so now it just start from zero current, and during that time, S is on, L charging. Okay, so you have dTs. So this is no different than the previous operating conditions. And again, for that cycle, which is in the discontinuous conduction mode or in the boundary one, this was 1 minus d times Ts. But now our duty cycle is reduced, or maybe our current has reduced, so we are waiting for the next cycle to come, but it doesn't come, and our inductor discharges and just touches the zero before our full full cycle starts again. So this is not the time wise, it is not 1 minus dTs, but it is shorter, and textbook it is defined as delta 1 time Ts. Anyway, So in this time S is off, okay, and L discharging. So in this mode you are supplying still some current to your inductor, so L is giving its charge to the capacitor. But this mode, that is interesting, so that mode, this is interesting. Okay, this is where, let me draw the circuit again. So you don't have any current coming from the source side until here, so that is the only part that you are using some power from the source. And then you have the inductor and the capacitor, okay, and in that cycle, yes, you don't have any power coming from the source side, but you still have some power or some current coming from the inductor in this part. But in that third part, okay, so your inductor current is already finished, okay, and then you have your R and you have your C, and in the third part, so basically the capacitor, okay, here capacitor is supplying the load. Okay, so in this time you don't have any inductor current, you don't have a diode current or switch current, but it is just an RC circuit. And because of that RC circuit, one disadvantage of discontinuous conduction mode, depending on how long that discontinuous conduction mode is, your capacitor voltage is decaying. So if you don't want to have a large voltage ripple at the output, you need to increase the size of the capacitor. Okay, so your capacitor should have enough charge or enough capacity to supply the load for that discontinuous conduction mode. Okay, again, in the textbooks there are some derivations, but as one disadvantage of DCM, if you just keep the capacitor size constant, then that will cause more voltage ripples at the output. Or if you want to keep the output voltage ripples controlled, then you need to increase the size of the capacitor. So let's have a look at not the ripple but the average voltage changes. Okay, in general, if you just keep the duty cycle and your input voltage constant, as you get into the DCM at steady state, the output voltage starts climbing up. So let's have a look at this waveform, right? So here, that curve, can be similar to, that is, the current on that axis. So this is the boundary, okay, that dashed line is the boundary from continuous conduction mode to discontinuous conduction mode. So it was basically the previous slide. So this is the ratio of the output voltage to your input voltage. Again, if you are operating at CCM, okay, and if this, let's say your duty cycle is at 0.1, so your ratio is also 0.1. Right, but that is valid for CCM. Okay, and actually if you just get into the discontinuous conduction mode, this is not a linear relation anymore, so it just starts climbing up and up. So you can derive it yourselves as well, but the derivations are available in the textbook. I don't want to get into detail of that characteristics. However, if you just move to 0.3 or 0.5, so 0.5 is where you have the highest boundary current. So this is the point easiest to get into the discontinuous conduction mode. So again, it is constant through different currents in the CCM, but if your current is reducing, and then you are getting into the discontinuous conduction mode, and then your output voltage starts climbing up. Okay, again, it is not a bad thing, but that is basically, if this is your DC-DC converter, and let's say if this is V in and if you want to have V out, okay, I mean the important thing from this figure is if you just give duty cycle blindly like an open loop control, and let's say if you have 12 volts and if you want to get 6 volts, and if you are just applying 0.5 duty cycle and if you want to obtain 6 volts, that is only valid if you are operating at the DCM. If somehow your load changes, or I don't know, if your input voltage changes, even if you are applying 0.5 duty cycle, you can get a higher output voltage. So that is why in most of the converters we have a feedback. We are measuring the V out, okay, then you have some kind of controller, and actually it is comparing it with some kind of reference voltage, and then depending on your actual output voltage, and you apply some duty cycle. So even if your output voltage starts climbing due to the discontinuous conduction mode, you can reduce the duty cycle still, and you can keep it at constant voltage. So that transition is important, just to show the requirement for a controller in DC-DC converter. And now let's have a look at from the other side. So now I want to keep the output voltage constant. So what should be the duty cycle? So how does that controller needs to operate? So here again, this is a different representation. If you are again, and that range is that area is CCM, and under that dash line it is the DCM mode. So if you are operating at the CCM, and if this is your, I don't know, VD to VO ratio, or VO to VD ratio is 0.5, like you want to have 6 volts from a 12 volt supply, then you can keep the duty cycle constant. But if you are getting into the discontinuous conduction mode, you need to keep the duty cycle lower and lower. Okay, as long as you reduce your duty cycle, it is still possible to keep output voltage constant. Of course, you are not trying to program it, or you don't have to write all those equations into your converter. And once you have the feedback loop, once you have some kind of generic controllers, actually the controllers does that automatically, because if you keep the duty cycle constant, then you will have some errors, and the error will get larger and larger, so the controller needs to reduce the duty cycle. So let's stop here, and in the next lecture we will talk about the voltage ripples.